All right, I'll get started with the introduction. So I've taken to writing these introductions down, and I also need to have glasses while I read them, and I didn't need to do that. But this one I could do without the piece of paper, but I'd like to make sure I get everything right. I think you know if you're a regular attendee of these series, or if you're coming to this series in particular because you saw the article in the paper, or things like the environment or climate change are important to you. This is a good time to let you know that we have these series of talks. It's phrased as what physicists do. So it's physicists dealing with a variety of issues and often problems and concerns that we have. So every semester we certainly have 2 or 3 of the talks are about things like energy or climate, because physics is a way for us to know the world around us and to study it. But of course we also have our wonderful astronomy talks at the frontiers of material science, and just the variety that the Bay Area and California offers us in terms of wonderful speakers to bring in here. We're very fortunate today to have Dr. Frank Hsu as a speaker. He holds the title University Professor in the University of California system. So this is a very prestigious title. I was joking with him saying that I knew that he was at Berkeley and now is at San Diego. Does that mean the title just lets him go to any University of California campus and claim an office? Which it isn't quite like that, but if you are a university professor, they will want you to have an office on their campus. And currently he's at San Diego. He received his bachelor's at MIT and his PhD from Harvard. During his career, he literally wrote the book on astrophysics. I say this personally, and I have a small sadness that I forgot to bring in my wife's copy of his book, The Physical Universe. This undergraduate text was used a lot by graduate students, and he wrote a 2-volume set that was meant for graduate students as well. But The Physical Universe was this book that was so eloquent in its simplicity of how to attack problems in astronomy through the tools of physics, that it was the canonical book for those of us studying and cramming for that exam where you literally are supposed to know all of astrophysics by the time you're 2 years into graduate school, that we all use that book to look at how a physicist's mind would look at any problem in astronomy. And as I said, my wife's mad at me because I meant to bring in the book to have Frank sign something to her, but she'll forgive me, I hope. So, in 1976, he spoke in this series. And as you look at his career, there are many different topics that he could have spoken on. He spoke about what's called spiral density wave theory, or an understanding of the physics behind why galaxies make these beautiful pinwheel spiral shapes. He also wrote the seminal paper in understanding the collapse of a cloud to form a star, so stellar formation and stellar evolution. He also studied meteorites and looked at their origin. The idea here is, as a scientist, Frank Hsu has addressed the big issues. He has many accolades. He was the former president of the American Astronomical Society. He was a member of the National. He is a member of the. You don't get kicked out. He is a member of the National Academy of Sciences and a fellow of the American Academy of Arts and Sciences. He's also the recipient of more awards than I can mention, but I'll mention the Bruce Medalists, which we have the world's foremost historian on the Bruce Medalists in the audience today, and he won the Shaw Prize. As we said, he turns his attention with the mind of a physicist looking at problems, and in recent years he's turned his attention to looking at the problem which may concern all of us, climate change. And as you know, he'll be talking about a topic called biochar, and the title of his talk is The Future of Energy. Please give a warm welcome for Dr. Frank Hsu.
Thank you, Scott. Wonderful to be back. living in Southern California, you kind of forget what a civilized place is like. But anyway, it's wonderful to be back in Northern California. Today, I'm going to talk about what to do about climate change. Not so much about climate change, but what to do about it. And I have some strong opinions, okay, on this topic, but I'll leave it to the talk to explain it. Anyway, this is the work of a team that we formed. We call ourselves the HX team. HX stands for heat exchanger. And that was formed about 6 years ago. I won't name all the people down here. But they are an eclectic group. Some from California, some from Taiwan, some from Hong Kong, some from University of Michigan, some from all over, okay? And people, many of them are astronomers, actually. You will recognize some names there, perhaps. Anyway, about 6 years ago, I got really concerned about climate change. I'd always worried about it, but I felt that things weren't progressing as fast as I had hoped when I was your age, okay? I thought the problem would be solved, but it hasn't been. And here are some consequences, or at least some connections. We know about the ongoing drought in California, which is budding on to be the worst in 1,000 years. If it's not caused by climate change, it's undoubtedly aggravated by it. Climate change does both. It makes droughts, and it also has too much rain sometimes. It's the extreme events that are the most dangerous, creating tremendous forest fires, or in Sonoma County, the sudden death of literally hundreds of thousands of tan oaks when things get too wet. Okay, there's a mold that kills these trees. And then, of course, they become tinder for possible fires. So we have an approach, we think, that can smooth out these extremes, at least in terms of their effect on vegetation, on trees, okay? And this is biochar. I chose to talk about this particular topic because actually Sonoma County is one of the biochar centers of the world, okay? There are many people here working on this problem. And we just have a method of producing it fast and in large quantities. Enough, we think, we hope, so that it can be a help in a global way. So this is an outline of the talk. I'll start with the 4 E's. Energy. Once you bring in energy, it affects economics. It lies at the base of all economics endeavors. Once you have economics as a concern, you automatically bring in environment, because people are always tempted to cut corners, okay, and to dump their waste in places that they shouldn't be dumping it, okay? And of course, once you have these three, there's a question of those who suffer and those who should pay, okay? So there's a question of ethics. How do we regard this problem? And I'll talk briefly about the alternative energies for the future. And everybody knows this list, and everybody knows the objections that the opposite side has to these lists. Okay, wind and solar, it's very diffuse, okay, has low energy density in physicist jargon, and it's non-dispatchable. That means you can't necessarily count on it when you want to use it. It may be cloudy, the wind may not be blowing, okay? So you need backup in that case. There's hydroelectric. Unfortunately, it's mostly saturated for reasons that we'll discuss. There's current nuclear, which is opposed by environmentalists, I think for reasonable reasons. And industry, frankly, hasn't been very upfront about it either. The present industry practice is, in fact, unsustainable. Okay. I'm not going to talk about this topic, even though our group also works on new nuclear kinds of reactors, but I'll just mention some of the problems. And then bioenergy. When you mention bioenergy, most people think of biotech, okay? And the problem there is basically biology is chemistry at room temperature. Chemistry at room temperature is very slow, okay? So and energy is a huge problem. So although it's great for making drugs, you need high throughput, and I see that as a fundamental problem. So we'll take a somewhat different approach when it comes to bioenergy. Then I'll talk about 3 applications of this last topic. One is to replace fossil fuels with synfuels made by supertorrefaction. That's a word we use for the process that I'll be talking about. How to reverse climate change, actually not only have 0 carbon emissions, but actually have negative carbon emission. So you can actually enjoy, maybe, by the end of the century, okay, the climate that I enjoyed when I was a kid. That comes by burying biochar, and then finally how we actually bridge from petrochemicals to biocarbon. We forget sometimes that petrochemicals are the basis of much of the material world, okay, that we live today. Look at that bottle, okay, it's made from oil. So if we're going to stop using oil, we better tell the oil company what they should do with their stuff, because they're not going to stop using it otherwise. Okay, now, whenever you talk about such a topic, it's mostly gloom and doom, okay? And I don't want to do that. So I want to give you a story, a joke, to start. It sort of summarizes the bottom line of my talk, okay? So here's the joke. Climate change skeptic and a climate change scientist walk into a bar, just happenstance together. And the skeptic says to the bartender, he says, "Give me the strongest drink that you have." So the bartender looks up, pulls down a bottle. He says, "This bottle is 97% ethanol, but it's going to be a little pricier than the normal." The skeptic slams his hand on the bar and says, "I'm not going to pay," and he storms out of the bar, okay? And so the scientist turns to the bartender and he says, "What's the trouble with these guys? You show them the proof and they don't buy it." Now, what's the point of the story? The point of the story is not necessarily that the climate change scientist doesn't believe that this is a strong drink or that he doesn't need a strong drink. He just doesn't like this particular solution, this bit about 97% ethanol. And he doesn't like the fact that it's going to cost him more. And that's not unreasonable, to be frank. There are many things that are suggested by environmentalists. I consider myself an environmentalist, and I think they're not well thought through, okay? That are not necessarily things that are unreasonable to object to. I think on both sides, people have to start listening better to what the other side is listening. Because after all, as JFK said, we all live on this small planet, okay? And we all have to take care of it. And we cannot, constantly saying, "Oh, you're evil, you're stupid." That gets us nowhere. We have to start talking and trying to find some middle ground where we can go forward. Okay, so I'll begin by reminding people that a very famous economist, John Maynard Keynes, was perhaps one of the first to eloquently point out the close connection between energy and economics. This isn't a direct quote, but it's kind of a summary of many things that he wrote. Basically, his basic point was, for millennia, for thousands of years, until the Industrial Revolution, sparked by coal burning, the only way humans made economic progress was to enslave other peoples. Okay? So here is a slide, a graph that demonstrates this point. So of course we all know the Industrial Revolution began in Great Britain. So this is a slide of the per capita income in Great Britain going back over 2,000 years. Okay? So at zero, what was the average per capita income? It was roughly, in US dollars, $1990, it was roughly a few $100s a year. If you think about that, it's just $1 a day. Okay. People were living on $1 a day. Now, after a while, they started enslaving people, and sure enough, in Britain, the average income improved until it was about $2 a day. $2 a day. And then it really took off after the Industrial Revolution, because people found that you could burn something called coal in the steam engine, and the steam engine could do many things that people could do much faster and much more accurately, etc. And then things really took off, and it hasn't stopped, okay? Just took off until around the mid-19th century, 1860s in the United States, 1830s in Great Britain, it became unprofitable to keep slaves. And so slavery was abolished. It was as much a point of economics as it was ethics. They just became uncompetitive to do things that way. And when I talk about slavery, I'm not just talking about, one race enslaving another race. I'm talking about people enslaving women, children, okay? And that was all gotten rid of because of the Industrial Revolution, because of coal burning, and later oil and natural gas. Okay? So it's not that fossil fuels are this evil thing. We wouldn't have today, your cell phones, your computers, without fossil fuels. That's a fact. Second, what we should not forget is that the Industrial Revolution has not come to everybody in the world. There are 2 billion people in the world that live on less than $2 a day. Okay? So they have aspirations to join the Industrial Revolution, to have a better life. Right? And we cannot impede their aspirations. That's my view. Okay? So, what can these people do? If you talk about the labor of one adult for 1 hour, how much work is that? Well, it's easy to estimate. A human being is about, a good athlete is about 2/10 of a horsepower. So you can say, if you had to spend 2/10 of a horsepower for 1 hour, how much work can you do? Well, it's roughly the same as if you burn a handful of coal, or if you try to catch 40,000 cubic meters of wind. Okay? So you give this choice to these people. What are they going to choose? It's a no-brainer. Are you going to do 1 hour back-breaking work, or are you going to burn that handful of coal? They're going to burn that handful of coal. There's no stopping them. It's ridiculous to think that they're going to try to capture 50,000 cubic meters of wind, especially since when they want to cook, it's not blowing. What are they going to do? Okay, so I think we have to keep that in mind when we, as a rich country, try to tell other countries what kind of forms of energy they have to use. Okay, so what are the alternative energies? Well, let's just, before I talk about the future, let's just talk about the past, okay? What was the breakdown of energy in 1973? Whoops. Yeah.
I plugged that in.
Yeah. Which was the year of the first oil crisis, okay, Arab-Israeli war. What was the breakdown? Here it is. Oil, 46%. You can read it for yourself. Coal, 24.6%. This is all energy in the whole world. Natural gas, 16.1%. Nuclear, 0.9%. Hydro, 1.8%. Biofuels and waste, 10.5%. Wind, solar, geothermal, negligible, 0.1%. What is it in the latest things that you can find in the International Energy Agency. So this is the latest I could pull up, 2012, okay? It's roughly doubled in total, a little more than double. There's a million tons of oil equivalents. What is it? It's still about the same. Okay, it's switched a little. We actually burn a little more coal, a little less oil, and a lot more natural gas because of new techniques of extracting natural gas. Nuclear has expanded from 0.9% to 4.8%. Hydro has gone up from 1.8 to 2.8. Biofuels has held roughly constant. And wind, solar, and geothermal has increased by a tremendous amount, tenfold. But it's still only 1.1% of the total. 40 years, and it's only gone up 1%. How is it possible in the next 40 years, which are critical, can these sources replace all this? Many people think it's not possible, including environmentalists. Okay. So that's a basic problem. And when you talk about bioenergy here, what are we talking about? Are we talking about, ethanol? No, mostly that 10% are people in rural areas burning wood, burning dung, as they've done for the past 5,000 years. That's what it mostly is. And so we must be able to do better. It is by far the largest segment here. So, we shouldn't ignore it. I'm not saying we should stop doing these things. We should not ignore this, nor this. Okay, so this is, I understand, a physics undergraduate seminar. Many undergraduate physicists here. So I want to tell you why, from a physicist's point of view, things are the way it is. This slide is kind of busy, so those of you who don't want to listen, don't listen to the reasoning, just listen to the conclusion, okay? So the first thing a physicist would ask is, how much energy do different sources have in a given volume of space? Let's say a cubic meter of volume. How much energy does it have? Obviously, if it has less, or seemingly obviously, if it has less, it's less desirable in some sense. If it has more, it must be cheaper. Not quite, for reasons I'll shortly go into. So this is a very simple concept. So in a cubic meter of air, how much air is that? That's 1.225 kilograms. And if you move that at the speed of a good wind turbine site, 7 meters per second, every physicist knows how to calculate the kinetic energy in that, okay? 1/2 mv squared is 30 joules per cubic meter. Now, how much electricity can you generate from that? It's not 100%. If it were 100%, your blades would have to block everything. If it blocks everything, it just goes around you. So then you get zero. On the other hand, your blades can't do nothing, so it must be also zero at the other end. So it must be a curve that peaks somewhere in the middle, and if you guess, probably 50%. That's right. If you're really smart, you might get to 56, 58%. But that's about it. Okay? So you can do this for all these things. What about hydro? Well, water is much denser than air. In a cubic meter of water, you have 1,000 kilograms. If you let it fall through 100 meters of free fall, it gets to a lot higher speed. So it may not be surprising that hydro is literally hundreds of thousands times better than wind. Okay, in this metric. Natural gas. How do you generate electricity with natural gas? You do it by making a wind. You burn it, it becomes hot, it expands, you push it past the turbine, it can generate electricity the same way that a wind turbine does. Well, chemical energy is much greater than normal mechanical energy. Mechanical energy is measured in tens of joules per kilogram. Right? That's why we chose the joule as the mechanical unit. Chemical energy, any chemist will tell you, is measured in tens of megajoules per kilogram. So it's 1,000,000 times more powerful than mechanical. So that's why even natural gas with a very low density, all right, is literally, millions of times more than wind. Coal is even denser than gas. It's so it's hundreds of times better than natural gas. Oil is even denser, so it's twice as good as coal. Moreover, you can do this. You can do it for nuclear. Okay? You use old nuclear like we use today. We're only using 0.7% of uranium. It's still trillions of times better. And if you use new nuclear, literally hundreds of trillions of times better. So why is it then all these things are roughly the same cost? When anybody can do this calculation, everybody knows these numbers. Why is it everything is competitive, right, when it comes to producing electricity? You could say, well, maybe it's a collusion. These guys, it's some kind of conspiracy. And to some extent, that's true. But most of it is actually physics. And it is because all these methods use a turbine to generate electricity. Okay? So a turbine, you turn with air rushing past it or gas rushing past it. It turns a magnet inside a core of wire. If you learn Faraday's law, you know that will create electricity. That's how it's done. Well, a wind turbine is nothing but a turbine and some lots of gears. So they don't have to spend any money on anything else. With a hydro, it's not just a turbine. You have to build that big concrete dam. You have to find the right place to do it. So even though it is still cheaper, okay, but all the dams have been built. So it's stalled out. Natural gas has a huge advantage because it's also a gas to start with. You heat it up, it expands. You can make it expand much faster than 7 meters per second. You can pressurize it. So it's, wind cannot beat natural gas today. That's the problem in the United States. Coal heats water to become steam, and that does it. Steam is much worse than natural gas. It's corrosive at high temperature. You need to have it at high pressures. Coal has other disadvantages. So even though it's cheaper than natural gas, actually coal-fired power plants today are a little too expensive compared to natural gas. And you can say, well, what about these guys? It's the same problem. You see, it doesn't matter how good your boiler is. You can just have it this small, you can have it this room. When the turbines are the cost, what does it matter? That's the problem with nuclear. It's because we use it to generate electricity by turbine electricity. So if all the cost is in the turbines, you're going to at best be comparable. And if people don't like you, then you're going to be worse because they're going to bring you to court over every issue. Okay? And that's what's happened to nuclear. So that's a long explanation. So there is one thing here that I think all astronomers like, including me, which is solar voltaics. And you just notice it doesn't have the same units as the others. Not joules per cubic meters, watts per meter squared. Every meter square during noon, if there are no clouds on Earth, you can point a solar panel so that if you have a square meter of that, you can generate 1,400 watts. It's power, not energy. Of course, its efficiency is not as high, but it's very clean. So the problem with these guys, which have a huge advantage economically over wind, not so much over hydro. Hydro is really the best thing you can do. Look at it, 90% efficiency. Is over here. How much CO2 do you emit per gigajoule of energy that you receive? You can see that coal is really bad. That's why everybody wants to get rid of coal. Oil is not so bad, but we don't ever burn oil to generate electricity unless you're desperate. Okay, or you're living on an island where there's no other way to get energy there. So Hawaii will burn oil. Oil is the most expensive fossil fuel. Per unit energy, is 10 times more than coal and 3 times more than natural gas. So nobody in their right mind would burn oil to generate electricity. It's used for transportation. It's very convenient, right? It's not as good as natural gas. So that's the choice that people are making. And I frankly don't understand it. You know, if this is so much better than that, isn't this and this so much better than that? That doesn't make sense. Right? Why are we doing this? Well, because there's lots of it, and the U.S. can bring it on board very quickly. But that's not true of the rest of the world. And by the time you ship it to Asia, let's say, it's 5 times the price it is in the United States. So nobody in Asia is going to go this way, or Africa, or Brazil. So if we want to forecast the future, let's see how experts did in the past. Okay? So this is another fairly busy slide. This is prior 30-year forecasts. Experts looking 30 years into the future as to what is the future for fossil fuel and nuclear energy. At one point, everybody thought it was either going to be one or the other. Now, nuclear energy peaked at 50% because electricity generation is only 50% of total energy. The rest is in transportation, heating, etc. So, in the beginning, everyone was very optimistic about nuclear power and thought it would be 50%. Later, because of various reasons, including accidents, like 3 Mile Island, like Chernobyl, and then, of course, Fukushima, has dropped precipitously. So this is everybody here looking 30 years out in the future, predicting what nuclear would be. Okay? And you can see that when I was in college and beginning faculty member, everyone thought it would sort of stabilize at 20%. Well, it's down to less than 5% today. And that's the prediction. It's only going to stay at that. Well, if it stays at that, hello, climate change. Okay, here is what people think of fossil fuels. Now, this has many, many people looking at it. I'll just point to 2 different groups. Here's Greenpeace. Can't get much greener than Greenpeace. And this is Shell International. You can't get more, I don't know what, of fossil fuel than Shell. Okay? They're not that far apart, are they? Okay? Everybody sort of predicts 30 years from now, we'll still be using 80-some% fossil fuels. Even Greenpeace. Why? Because everybody knows the background. So how are we going to get to 0, which we absolutely need to, or even negative if we want to? So the current line is, well, let's do it with renewables. Well, let's see what people predict for renewables, okay, through the years. At first, people were rather pessimistic, just a few percent, and then it became, 10%. Then today, people like 15%, or here's Greenpeace, here's Shell International. 15%, and by mid-century, essentially, of what we use, what we need. So what does that mean? That means if we really think we're going to depend on a renewables-only future, it means a 6 times reduction, either of population, which isn't going to happen, or 6 times reduction of average standard of living. Okay? There are some people that think we should do that. I won't argue with them. I sort of think we do need to cut back. But 6 times, think about it. How much do you surf on the internet? Okay, if it's 6 hours a day, 1 hour. Okay? How much often do you bathe? 1/6 as much. Okay, it's not easy. So this is the problem, right? The climate change skeptics in developing nations often are opposed, because not that they oppose the idea that climate change will happen, they're opposed to the solutions that are being proposed. Our solutions just are not acceptable to a large fraction of the people on Earth. That's a fact. Okay, I can't change it. Many of you may try to change it, but in fact, that's a problem. Okay, so one approach. And that is, if we can't use fossil fuels, can we make fossil fuels, but with today's biomass? So how are fossil fuels made? It's very simple. 300 million years ago, the carbon dioxide in the atmosphere was 10 times what it is today. Not 400 parts per million, 4,000 parts per million. We know carbon dioxide at 4,000 parts per million. Yes, the climate change stuff takes away. The trees grow like crazy. They get very, very big. Some of them fall into lakes or get buried in volcanoes where there's no oxygen. And then as they press deeper and deeper into the earth, they get heated up. And that's the condition in which you can drive out the water in biomass, the volatile material, until it becomes coal. Right? If you have a little bit of water, because at tremendous depth, the pressure is very high, even at 200 degrees Celsius, water is still a liquid, it can react with the coal, so you produce, we don't know exactly how, we're beginning to reproduce some of it in the laboratory, into oil. And if it gets too hot, it becomes natural gas. So the question is, can we do the same thing on Earth today, except use plants that have died, that would decay and put their carbon dioxide back into the atmosphere, or as methane, which is even worse. We stop that from happening by making charcoal out of it. Plus, if we can, the byproducts of things similar to oil and natural gas. So the way to do it is to do it with a liquid. We use molten salt. Salts are anything basically from the left-hand side of the periodic table combined with something on the right-hand side of the periodic table. They're very stable substances because it's hard for any element in between to get in between them and cause a reaction. So you can take them to high temperatures, they won't decompose. And if you take it to high enough temperature, instead of requiring 300 million years, you can do it in 10 minutes. And that's what we do. In 10 minutes, we reproduce what nature does. Okay? Not over the whole earth, only in smaller batches, but nevertheless, that's the event. So the potential here is disruptive technology to replace fossil fuels with synfuels, which are not only carbon neutral, but have the potential of being carbon negative if you don't burn them. And the social impact, of course, the hope is to reverse climate change within this century. You know, my generation really should feel some guilt. We had a tremendous life. We had tremendous opportunities. I hate to leave this earth thinking that we left it in such a bad condition that the people in this room, or your children, or your grandchildren, will never see that in their lifetime. I think we owe it to the younger generation to do better. So, let me jump to the next topic, replacing fossil fuels with synfuels. So here's a tabletop model that we built just to demonstrate the principle. So here is a inlet port, which you can open up by opening up that latch, and then putting biomass, any form of biomass, into a porous barrel. Think of it as a wine barrel, except it's leaky, it's got holes punched through it. And then we use sprockets and chains. This is just an expensive bicycle that we crank. We put the crank at a low enough level so that a grade school child can run this machine. It's that simple. Takes it over here where we have a bucket that will keep that 300 degrees or higher. Inside there's salt. It's not table salt. There are many different kinds of salt that you can use. And you just dip it. Once it goes underneath the salt, there's no more air. It's like being underwater. So it's just like being heated without access to oxygen. So the same thing happens. The volatiles are driven out. We capture the volatiles, bubble it through here to its own mixture. Capture it, what we don't capture comes out here, and that is something similar to natural gas. You can still burn it. It's not natural gas, but it's kind of gas that you can burn. So we get all three things: liquids, solids, and gases. After 10 minutes, the cooking is done. Our cooking is terrible. Everything we cook, we char. Okay? So we take the thing, it's all covered in salt, so you don't have to worry about it bursting into flames. It doesn't. You wash it with water. Many salts is water soluble. You don't want salty charcoal, okay? You want to wash it clean because that salt is worth money. And you wash it as many times as you want to get it as clean as you want, and then you transfer the salt water into here. It vaporizes the water, we recover the salt. The water we also keep, okay? Because it's needed for washing. Everything is self-contained. So what do we put through here? Well, here is a plant that's the fastest growing plant in the world. It's bamboo. You put it through here, it comes out bamboo charcoal. Here's an invasive species planted all over Southeast Asia because originally it was good for firewood. Nobody cooks with firewood in Asia anymore. Everybody uses natural gas. So it's taken over because this has adaptive advantages over native plants. So there's lots of this stuff. We take it. After 10 minutes, it becomes charcoal. It's called lucano. It's native to Mexico. Here's a banana peel. You can toss banana peel. You can toss orange peel. It'll come out as charcoal. So what kind of charcoal can we make? Well, if we submerge it under 300 degrees salt, we get a coal replacement. We get what we call eco coal. And that's just as good as natural coal, but it doesn't have all the nasty stuff. It doesn't have mercury, it doesn't have lead, it doesn't have all that stuff that's associated with coal. Why? Because it wasn't dug out of the ground. If you dig something out of the ground, you're going to get little stones, and those little stones have all that nasty stuff when you burn it in the furnace. Plants don't take up that stuff, so it's much better. So it's carbon neutral if you burn it. If you put it through 450 degrees, so you get the much better kind of charcoal, which we call biochar. Other people call it biochar. It can be used as a soil amendment. Now, charcoal does not rot. Okay? You can have a bag of charcoal in your garage. I'm sure many of you do. Even for a year, even for 1,000 years, it's not going to rot. You leave that same thing as a banana peel. After a few days, it starts to rot. So once you sequester it in that form, it stays in that form. It's going to last thousands of years, maybe millions of years. After all, coal has not rotted. It dates back to 300 million years. Okay? So it is a kind of permanent sequestration. It becomes carbon negative if whatever you use today, you grow back next year and you do it again. So gradually, you can use plants to pull the carbon dioxide out of the atmosphere, which they do anyway, and sequester it. It's sort of reversing. You can think of it as a reverse of what we've been doing all these centuries. We've been digging stuff that was made hundreds of millions of years ago, burning it, putting it back into the atmosphere. Now we've got to reverse that process. We've got to put all that stuff we dug out of the ground back into the ground as coal, charcoal. That's it. Simple as that. Now, if you pre-treat it, you can make it into an even higher form of charcoal called activated carbon. Activated carbon is a miraculous material. Very old. It's what today people will call nano material. Okay? That's just fancy talk for something that has a lot of holes. It's very porous. How porous is it? Well, if you were to put molecules in there, you can say how much surface area has it stuck to. You can measure it with a technique called jet, Brownell, Emmett, Teller. And we made, on our first try, activated carbon that had more than 2,000 meters squared per gram. What does that mean? It means if I have a gram of this material, it has more area than all the wall and ceiling and floor space of this room. How can that be? It's because it has lots and lots of holes. It's not just the surface that you see, it's all those pores. How much is 2,000 meters squared per gram? It's phenomenal. It is, if you had 1.5 grams of it, you would have the same collecting area as the Alma telescope, the largest telescope that astronomers have built, right, for billions of dollars, right, costing less than a penny. You have that collecting area, not for photons, but for molecules. So it's very useful in all sorts of chemical applications, energy applications as well. So that's what is the highest stuff we can make. Okay, what is the bioliquids we get? Well, we get mostly two things. One is methanol. Methanol, another word for it is wood alcohol. That's what you got when you distill wood this way. Okay, you got wood alcohol. Methanol is a marginally good fuel, but you can make it even better. Then acetic acid. I don't have to tell people in Sonoma County that acetic acid is basically vinegar, right? It's what wine turns into if you expose it to air. So, acetic acid, you may not realize, is a fuel. You can burn it. Not very good to burn it because it's an acid, right? It's going to corrode your material. So you should make it into something better. Well, we can, in one step, naturally, because of the salt we use, turn it into acetone. Clearly has something to do with acetic acid, because it has the same prefix, right? Acetone is a 100-octane fuel, but don't ever put it into your car, because it'll dissolve all the rubber baskets. It's a very good solvent. Chemists use it as a So the reason it's a very good solvent is chemistry. I won't go into that. But you can turn it into a very good fuel. Turns out, by having another kind of thing, not activated carbon, but a mineral that has lots of holes in it, adding heat, you can take 3 acetone molecules and make it into a hydrocarbon, okay, which is C9H12. That is something like gasoline. It's in fact very similar to aviation fuel. Okay, why is fossil fuels so good and alcohols not so good? Why is it that the car companies object to even, you're putting 10% ethanol into gasoline? It's because all these other things have oxygen in them. They not only have carbon and hydrogen. Alcohols have oxygen in them. Acids have oxygen in them. That oxygen makes it much, much worse in terms of corrosion, in terms of fuel properties. You got to get that oxygen out. That's hard, but it's possible. And people know how to do it. We know how to do it. Other people know how to do it. There's a company in West Lafayette, Indiana, which I grew up, that takes this stuff and makes it into jet fuel, aviation fuel. It's not good in the car because its vapor pressure is too low. Now, if you put it in your car, it won't ignite. So you have to put in a lower carbon, hydrocarbon. But airplanes fly very high where the pressure is low, so it's fine. It's great for airplane fuel. It's better. It's FFAA approved. So you can, with enough work, take biomass and convert it into something very similar to gasoline or diesel, in the sense that it's a hydrocarbon, in the right range of hydrocarbons. And finally, syngas. You can burn for facility electricity and leftover for the surrounding neighborhood. So in addition to building that tabletop model, we built a batch process facility in Tsinghua University, where I was for 4 years. We use a batch process here just to control the odors better. Here's a melter tank containing 4 tons of salt, which we melt. We use electricity to melt it, but in the commercial thing, you would burn part of your charcoal to melt it. You pump it up with this pump that sits here. It's just a thing that whirls and it flings it up through these pipes into this tall space. But if it's not hot enough, you can add some more heat, bring it down into a cooker. It's really just a pot with a lid. Okay, and we put a basket of biomass into it, we close the lid, let the salt in. After 10 minutes, it's done. Okay, and we wash it. We use the wash. It's in these basins here. And wash it very clean so that less than 1/10 of 1% of what was originally in it is gone. If you want it better, just add more of these things. And you recover all of that salt except for that 1/10 of 1%. So what do you get? Wow, sorry, there's another very busy slide. So this is if we take 1 ton of lucina at 300 degrees for 10 minutes. Here's what we get. It's got to add up to 1,000 kilograms. As chemical engineers say, you got to check 2 things. You got to check mass is conserved. You got to check energy is conserved. So here's mass. It adds up to 1,000. A little less than half is in big enough pieces so that you can use it. Some part of it comes out in very small particles. In the trade, it's called fines, very fine particles. And some of it is in tar. It's as bad as it sounds, okay? It's in your salt. You got to burn it off. So that, if you multiply what it's worth in terms of megajoules per kilogram, gives you 10.6. This gives you 1 gigajoule. It turns out that 1 gigajoule is enough to run the process. So something that's a nuisance for us is a fuel. We burn it right in the salt so that it's 100% efficient. It's captured by the salt. That's our model. 0 waste. You want to be sustainable. What's the trick? The trick is you don't have any waste. If you don't have any waste, you can be sustainable. If you have waste, you should take care of it. Or you should pay somebody else to take care of it. Don't dump it into the atmosphere. Don't dump it into the ocean. Right? So we make sure we have 0 waste. So we get rid of it. Some of the minor amounts are things that have a little bit of oxygen in it, but they can be burned in diesel engines. They're already used as diesel additives. Most of it is water, not surprising. Okay. And next is acetic acid, and then next is methanol. Acetic acid, I've already told you, we turn it acetone after a couple steps, it becomes this thing mesotylene. Methanol, we can turn into acetic acid, which then we turn into this. Or you can just burn it with the gases. It's so little, it might not be worth it. Some people might not think it's worth it. It has a low boiling point, so you can just burn it with everything else. So what are the gases that come out? There's carbon dioxide, not surprisingly. A little bit of methane, that's what mostly natural gas is. Lots of carbon monoxide. Carbon monoxide is incompletely combusted carbon dioxide, so you can burn it into that. And a little bit of hydrogen, so little, you can't even talk about kilograms. So if you ask how much is there, it's tiny compared to that. It's 0.3 gigajoules. And it turns out, maybe, somebody up there likes us. This amount, if you burn it, is more than enough electricity to run the plant. So everything is self-contained. Plus, have a little bit left over to give to the community. Yeah.
Yeah, Dr. Shu, this is fascinating. So I have a few questions. Maybe you were aggressive, if I could just...
Sure.
So your input is the plants. The plants have brought carbon dioxide. Is that, I'm not familiar with, is that about 100% of their carbon on plants is from carbon dioxide?
Basically, the machine that takes carbon dioxide and water, turn it into things that have C, H, and O as molecules.
Right.
So they do it with the sunlight. So ultimately, we're using sunlight. The energy is in the plant. We're not making any energy. Okay, it's already in the plant. So you say, why don't you burn the wood? Okay, why go through all? Because if you do this, you can produce much more useful things. The charcoal can be brought to a much higher flame temperature than the wood. Everybody knows you cannot extract steel out of rock with wood fire. You have to have a charcoal fire. That's how steel was discovered, because some of the carbon got in the iron and it became steel. So separating it makes it useful. It's not that we're getting energy. We're not. It's already there. But separating it makes it more useful.
And I didn't do the math, but that's 100%. You don't have
Yeah.
the worst thing that you mentioned is having the tar, and you said you burned it.
Yes,
You're
also
not-
the water.
What you don't want to do is make something that's, oh, how are we going to
Yeah.
deal with this particular thing?
Right. The thing that's sad is water. Water is not bad, right? It's perfectly clean. But you got to vaporize it to drive it out. Right? And when you vaporize it, it's not the temperature that matters so much. It's the latent heat. Water has a tremendous amount of heat that you need to add, even at 100 degrees Celsius, to turn it from a liquid to a gas. Okay. And that is almost impossible to recover. You can recover it by making cold water into hot, okay, but basically you've degraded that. So that's, but fortunately, that's only half a gigajoule. You already have one from the charcoal furnace. So that's most of what that goes into is to drive out the water. Okay, so let me give you, again for the students, the scope of the energy challenge. People think, oh, this is great, let's go do it. Not so easy. It's because we use a lot of energy today. There are 7 billion of us on Earth, going to be 9 billion, and we use a lot of energy. How much? So let me just give you one example. Electric vehicles, as an example. Everybody thinks, well, let's get rid of all the cars we have on the road with electric vehicles. Is that easy or not? Well, suppose you use an electrical vehicle, use a lithium-ion battery, 16 kilowatts to run it. How much lithium do you need? Well, it's in the form of lithium carbonate. You need about 50 kilograms of it. Each battery can be used for 1,000 to 2,000 discharges. This one can only be last maybe 500. So we haven't gotten to 1,000, 2,000. I'm giving you the benefit of the doubt here. Okay? It's within reach. All right? 1,000 to why then? Because you see, the lithium has to go from one electrode to the other. When it gets into the electrode, it's very hard to get it back out. So after it drops below a certain level, you can't use it anymore. People replace the battery. They throw it away. That lithium is gone. Okay, today. We should extract it back, as I said. People aren't being careful. They have waste. They shouldn't have it. So if you have 1,000 to 2,000 charges and you only run it once a day, you can quickly calculate. You can use it for 5 to 10 years before you have to buy a new battery. So if you use it for 5 or 10 years and it takes 50 kilograms, then it takes here 10 kilograms or here 5 kilograms per year to displace one gasoline or diesel car permanently. What physicists call steady state will take you that amount of lithium carbonate. This stuff, by the way, comes from the same place where the Alma telescope is. If you've ever been there, it's got lots of salt. Lots of it is lithium carbonate. Total world lithium carbonate production is 100 million kilograms per year. Great. Sounds like a lot. Well, you divide 100 million kilograms by 10 to 5 kilograms, you find the answer, 10 to 20 million cars. That's great. Take 20 million cars off the road. Well, unfortunately, the world has 1,000 million cars today, and by the mid-century, it's likely to have 2,000 million cars per day in the world. So, electrical vehicles, at best, are 1 to 2% of the petroleum burnt in cars. And that's not everything. Cars only put out about 10%. So you're solving a 0.1 to 0.2% problem. This is a huge effort. It's a very admirable effort. And brilliant people like Elon Musk are involved in this. It's worth it, yes, to do it. But don't think that that means we're all going to be driving electric cars soon. It's not going to happen. There isn't enough lithium in the world. So, what are the alternatives? That's the bigger problem. The alternative is, of course, you should have much better recycling of it. You shouldn't just throw those batteries away. You should try to get the lithium out of there. Or some electrolyte that's 100 to 50 times better. Are there such electrolytes? Yes. You can go back to Volta and we use salt, ordinary sea salt. It's good. But it doesn't burn at low temperatures. You wouldn't like to have it in your car. It's too heavy. So it can only be used for stationary application. People have talked about that. People are doing it for stationary, but not for cars. You can use molten metal, liquid sodium. Would you want that in your car? I don't think so. Okay? So, yes, people are making progress, tremendous progress on the battery frontier. But, it's going to be some while before we have anything as good as lithium batteries. People have been trying for decades, not succeeding. Here's something that young physicists should think about. Supercapacitors. You all learn about capacitors. What do they use? Gotta hold lots of charge. Gotta have lots of holes. Activated carbon. That's what they use. Or graphene, which is nanocarbon. This is already activated carbon. Nuclear batteries. People may not know that if you have a light that cannot fail, it's never a chemical battery. That's a nuclear battery. When there's a fire, you better be able to see that. That's run on tritium, which is a radioactive substance. Okay? The Russians use strontium-90. They get out nuclear reactors to light up lighthouses in the Arctic because they want to go through the Arctic. So, nuclear batteries, it's like Back to the Future, Doc running his car, the DeLorean. But that's only used today in space missions and niche applications. I don't think anybody, including me, I wouldn't want strontium-90 in my car because suppose you have an accident. It's all over the highway. It's all over you. So, here's the good thing, syn fuels. You have syn fuels, liquid fuels. People are already using it, methane, natural gas. You can burn it in such a way that it generates electricity directly. Things are not called batteries, they're called fuel cells, hydrogen fuel cells. Well, so you need about 10%, I didn't say it, but the amount that we get is about 11% the biomass. So if biomass could do everything, then you could, in fact, one fuel cell. How much biomass is there? This is a study done by the United Nations and the International Panel on Climate Change. And they did different scenarios of how much bioenergy could be available in mid-century in different parts of the world. And as a benchmark, the unit here is exajoules. In 2012, the total world use was 560. So if we could get the scenario too, we could, from plants, not impacting food production, in principle supply as much energy as we had in 2012. Okay. But it's much more likely we can only get half of it. Okay. So if you have half of it, how would you use it? And my personal advice is don't burn it. Don't use it as fuel. Bury it. Okay? That would mean it would take, if you made everything else carbon neutral, by other means, maybe 40 years to reverse climate change. Climate change is not irreversible. Don't listen to what people tell you. It is reversible. It's reversible in your lifetime, and you should do it. It's not a job for me. I'm not going to live 40 years. But I am helping you to get the start. Other people like me are helping you guys to start. You should do it for yourself. You should do it for your children. I think to get the rest of it neutral, like it or not, we're going to have to go to nuclear. So let me just give you an example that people are already starting to do this. Here are some pine trees that were killed in this part of Colorado called Hope. What a great name, Hope, Colorado. It's the site of an abandoned silver mine, abandoned a century ago. Now when you have silver, you have other nasty stuff. You have arsenic, terrible stuff, mercury, cadmium, zinc. Zinc is not so bad. The other three, really bad. You can tell nothing grew here for a century. It looked like this. This is where they threw the tailings. So in 2010, some people got a bright idea of taking a transportable torrefying unit, conventional one, up here, making this into charcoal and burying it. Okay? And they did it, and the next year it looked like this. All right? Well, couldn't grow for 100 years. Now it looks like this. So now it's carbon negative in two ways. It's the carbon that you put into the ground that you sequestered that would have been burnt into carbon dioxide if these trees ever caught on fire or turned into methane and carbon dioxide if they gradually rot. You've sequestered it for thousands of years. Plus, you've made plants grow where it didn't grow before. So you get extra carbon sequestration both below the ground and above the ground. How did that happen? It happened for a very simple reason. Physics again. Everything is physics. Okay? This thing has lots of holes. So these things are dangerous because they're water soluble. They're salts, it's water soluble. So when it rains, it goes into the holes. The holes are like a maze. When it comes back out during the dry season, mostly comes out as vapor. All that nasty stuff is left in the carbon. It's like a filter. It is a filter. That's why you use water filtration when the water is bad. That's what you use. That's number one. Number two, you can see it even out the water. When you got lots of rain, it would have run off. It's gone into the carbon. When you don't have rain, it comes out. Right? So it's even out the water distribution. That's the two things that it can do. This wasn't our discovery, but people here, people in Cornell, they know about this. What they lacked was a good machine. This only produces 0.23 tons per day. With one of our units, with two production lines, we can do 335 tons a day. Okay, better than, more than 1,000 times better. Stuff that's portable on trucks. Why? Because they're using flue gas. It's the same reason. We're using liquids. Liquids are much better, have much higher density than gases. That's why we get this fact of hundreds of thousands by using salt. So 335 tons per day, you can easily calculate if you have a 360 day, that will produce that many tons. If you put 100 tons per hectare, you probably don't need that much. But if it were that, you could remediate 1,206 hectares. How much land is that? That's 11 Sonoma State universities. Okay? So which would you rather do? Take this stuff, which in a coal-fired power plant might last at the rate of 400 tons an hour, just lasted a day or two. Or you remediate 11 Sonoma State University. It's a no-brainer, which is worth more. Okay? So that's why we should not burn them. Moreover, it takes out cadmium. People may not know. One of the batteries that's very common is a nickel-cadmium battery. If you have a cell phone, you're contributing to this problem. Cadmium is very poisonous, but we don't make those batteries here. China makes them. When we recycle them, they go back to China. They break these things open to extract what they can, and it gets into the water. 40% of the rice paddies in China are contaminated by above safe levels of cadmium. Don't think that because you don't see the pollution, it's not going somewhere. Batteries are dirty things. Okay? So, 40% of the rice paddies in China. So it turns out this stuff will decontaminate cadmium. In the worst cases, you might have to use bone char. You can throw bone into our machine and it will produce bone char. It's lots of phosphorus. Phosphorus will immobilize the cadmium. Anyway, so how much will we need? One of these machines is obviously not going to do it. So if you had 120,000 of these machines that was transportable to different sites, then in 3,000, that's over 40 years these machines will last. So you do them not in all 1 year, over 3,000 per year. In 40 years, you can get the carbon dioxide that you need to go back to the kind of atmosphere that I had as a child. If you made the rest of the system carbon neutral. So there's hope. It's not that there's no hope. Let me finish, because we're almost done, on the material sector. So what do we do about stuff like this? Well, there's an even higher end of carbon fibers, which we're going to build the first plant to do this, because it's the easiest to convince people that's possible to make money. Take bamboo, you turn it into charcoal, you turn it into activated carbon, you draw the fibers out of it, okay? You weave it into long threads of carbon fiber. You weave it into a fabric. Once you have a fabric, you can make anything. I'll show you one example. There's a wetsuit. There's a company in Hawaii. They make wetsuit out of this material, which I don't know who supplied them, maybe Taiwan, which has this technology. Yeah, neat looking stuff, okay? So how much is this worth, this fabric? It's about $20 a kilogram. If you burned it, it would be worth about 7 cents a kilogram. So that's why economically you shouldn't burn it. You should, if nothing else, make it into this. You know, we tell people, you should buy one of our machines. You can make money hand over fist. Okay? We just want to make these machines so people can be carbon negative. But people can make money. Here's an even faster way to make money. The fossil fuel industry can do this too. Why shouldn't they do it? The lesson here is stop burning fossil fuels. It's a great resource for the future. Just don't burn it. Okay. We should not rob future generations of this resource. Fossil fuels should move up the value chain. Okay. You can pyrolyze nylon into long fibers. I've gone to a company in Southern California that does this. Okay, we have a partnership with them. They make carbon fibers. You turn it to graphite at very high temperatures, it becomes stronger and lighter than steel. That's why Boeing is now making stuff out of this carbon fiber. You weave it into carbon fabric. Once you get a fabric, if you fill the spaces, you can make stuff that doesn't have holes into carbon-carbon composite, like this Lamborghini Sesto Elemental. So how much do these things cost? I'm not going to give you the actual price. I'll just tell you. I've done the math. It's about $1,000 a kilogram for this. If you burn oil, it's only worth $1 a kilogram. How dumb is it to burn oil when you can make it $1,000 a kilogram? Stuff that is strongest material that we know, light. If we're going to go into space, we're going to go to other planets. Definitely going to be with this material. The Italians are smart. They build the best car, the Lamborghini Sesto Elemental, with this. How much is that car worth? $10,000 a kilogram. Okay? What is Sesto Elemental? It's Italian for sixth element. Right? The ancients had 5 elements. We have many. But the sixth one is carbon. Sixth element. That's what we should be doing. We should not be burning. So let me find it out. Just put this on this up down for show. People can take this home as the message. Okay? I hope that I've given the young people in this room some ideas. Not all doom and gloom, but it's not easy either. Okay? Things shouldn't be easy. Every generation needs its challenge. My generation had its challenge. Your generation, this is your challenge. You've got to do it. Pull it off. We're all rooting for you.